Challenge day number 2 problems. We're going to start with number 1 here. So solving for h, and this is our typical setup that we've been seeing recently with our right triangles, and we have the altitude drawn in from the right angle to the hypotenuse of the big right triangle. And so this is where we can draw in our extra angles. So we got another 90-degree angle here. I'm going to put 1 arc mark up here, 2 down here, 1 here, and 2 there. So in the end, all of our triangles, since it's not specifically stated here, but all triangles are similar by angle-angle similarity. So that's why we're going to be allowed to set up and solve a proportion. Now, if we want to try to figure out which triangles to work with here, one thing to notice is we know quite a bit of information in this problem compared to some of our stereotypical problems that we've been working on. One thing in particular that I know a lot of students would gravitate towards is they would say, hey, why don't we look at the baby triangle and the mama triangle? Because they both use H, and we know these two sides in there. So that seems kind of like a natural fit. But let me show you what happens when we do that. So let's say we've got the baby triangle ratio. Let's go mama triangle ratio. And in the baby triangle, we know these two sides, the h and the 7.8. So if we set up a ratio, and I'll just start with the h first, because it doesn't matter for the first ratio. But if I were to label these, the h in the baby triangle is opposite the 2 arc marks, and the 7.8 is opposite the 90-degree angle. So now if I want to set up the mama ratio proportion here, so I need to go 2 numerator opposite 90 denominator. So opposite the 2 in the mama triangle is this piece. And we don't know how long that is. We know it's less than 14.6 because that's the whole hypotenuse here, but we don't know how far that really goes. So question mark. We could give it a new variable name, but then we'll have h's and some other new variable like x, and that's just really not going to work out well. Now, I do know the opposite side of the 90. I know this is 12.3, but again, I have no clue what to do here. So I'm not going to be able to use the baby and the mama triangles. So one thing I just want to point out to you is in the papa triangle, notice we know all 3 sides. That might have been something you didn't recognize. So the papa triangle is really a great triangle to refer to because we know all 3 sides. So does it really matter if we take the mama triangle with the papa triangle or the baby triangle with the papa triangle? In the end, it doesn't matter because we know all 3 sides of the papa triangle. So let's go back and do baby, but now with papa. So the baby, let me get this going on here. There we go. The baby, let's still use the h over 7.8. So again, this was opposite the 2. This was opposite the 90. So now in the papa triangle, what's opposite the 2? So here's the 2 in the papa. Opposite of it is this 12.3. Is opposite the 2. And then what is opposite the 90 in the papa triangle? So here's the big 90 in the papa. Opposite of it is this whole 14.6. So you can see in the end, when we cross multiply here, we'll get 14.6 times h times h. That doesn't look like multiplication. And then if we take 7.8 times 12.3, that gives us 95.94. And then we just got to divide the 14.6 over. So algebraically, this is a very nice problem to deal with here. So divide that over, and I get a really nasty number here. So I'm going to round it to 2 decimal places. It's 6.57 rounded to 2 decimal places. And there is our final answer for h. Now, if I had set up instead the baby ratio, but instead I had used the mama ratio, let me just show you what that would end up looking like here. Yeah, let's go ahead and keep that right there. So if we'd use mama with papa, I need to go 2 and 90 here. So in the mama triangle, what's opposite the 2 arc marks? Oh, but I still don't know that. Oh, so I can't do that. So backtrack a little further. We're not going to be able to use that specific ratio. So we got to start all the way back over with a mama ratio. So in the mama triangle, we knew the h and the 12.3. We're just going to have a different ratio here. So opposite the h in the Momma triangle is opposite the 1 arc. The 12.3 is opposite the 90. So now in the Papa triangle, we're going to have to use a different ratio compared to what we used in the baby triangle. So Papa triangle opposite the 1 is the 7.8. And opposite the 90 is again the 14.6. But once I cross multiply, I'm going to end up with the same exact problem. And in the end, I get that same approximate 6.57. So in the end, it didn't matter if we used Momma with Papa or baby with Papa. We got the same exact ratio, or the same exact answer, sorry. All right, the second problem. We are told in the diagram, quadrilaterals FBAG, which would be this quadrilateral right here, and CDEF, which is this guy right here. They are both rectangles. So if they're both rectangles, I'm going to go ahead and at least put some 90-degree angles in these rectangles. I can put a right angle up here at least. Now, notice C and E, they both get kind of split up. So, I mean, I can put a 90-degree angle here, but I don't know how that 90 gets split exactly. So I'm at least going to leave the 90s in here and at least put that 90 up here for this bigger rectangle. And notice that this angle and this angle are still technically two of the 90-degree angles in the big rectangle. Now, we got to figure out what the length is, or the height, if you want to, of DE here, of this part of the rectangle. Now, a thing that I kind of start to notice is I've got this little triangle here, and I've got this triangle here, and I've got, let's go a slightly different shade of color here, this triangle. And so I start to wonder, are these three triangles similar to each other? And so if they were similar, we would need to prove that they're similar first. And let me just throw in some extra angles in here. If this is a 90, this is a 90. If this is a 90, this is a 90. So both of those are 90 by the straight angle postulates because we have to have 180 degrees on these straight lines. And so now notice in those three triangles, we've established, oh, I went too far on that one. We've got three 90-degree angles. So we've got matching angles. Now we just need to establish, are there a second set of matching angles? So if this thing's a rectangle, if the big things are rectangle and the smaller things are rectangle, remember from our quadrilateral chapter that opposite sides are parallel in rectangles because rectangles are parallelograms. So the top and the bottom of the big rectangle are parallel. And really the left side and the right side are parallel to each other. But notice the left side of the big rectangle is also technically the left side of this smaller rectangle. So that means I'm allowed to put two parallel markings on side AG because AG is going to be parallel to BF, but BF is a part of CF altogether. And then likewise, GF down here, FG, is parallel to CD up here, but this is a part of this same segment down here. So really, this piece is going to be parallel to this piece. So all three of these pieces get to be parallel to one another. And so one thing I start to notice is that this angle is alternate interior congruent to this angle. And then not only that, but this angle is corresponding to this angle. And I could have even said that these two angles were alternate interior. So in the end, notice that all three of my triangles use that same singular arc mark. So all three of these triangles are similar by angle-angle similarity. Awesome. So now let's see if we can use some side ratios in a proportion to help us solve for this side. Now, it is great that we know one side of this big triangle. We know this 12. But if we look at the other two smaller triangles, we only know one side each. And really, we need to know two sides, right? Where could we use some extra information to get either AG or to get AB? And it's going to be this AB that we can kind of use here. So notice this whole top side's 12, which means this whole bottom side is also 12. Because remember, the opposite sides of rectangles are congruent. And so if this much is 7, then that means from F to G must be 5. And if from F to G is 5 in this smaller rectangle, then that means from A to B up here is also 5. So now we're going to get to use this small triangle ABC, and we're going to use it with this big triangle CDE. And now we can set up a proportion. All right, so let's start with the question mark. If you want to call this X, it doesn't really matter at this point, but I'll still keep calling it question mark. So I'll set up a question mark over 12 ratio, and the question mark is opposite the 1 angle marking that I've already established in there, and the 12 is opposite the, I didn't have any markings here. So if I wanted to, I could put 2 markings on there. So now I need to go to the small triangle and repeat 1 and 2. So opposite the 1 marking, there was my 1 marking, and the opposite of it is the 3. Opposite of the 2, which would have to be the angle that doesn't have any markings, is the 5. So now cross multiply, and we get 5 times question mark equals 36. Divide the 5 over, and the question mark is worth, I would honestly leave it as 36/5, but if you really, really wanted to, what is that? 7 1/5. You could express it that way, or that even comes out to be an exact decimal, 7.2. Any of those are perfectly fine. All right, let's move on to the next problem. Number 3. Ooh, an old dilation problem. Fun times. All right, so we've got polygon ABCD, which looks an awful lot like an isosceles trapezoid from last chapter, is reflected and dilated to polygon PQRS. So this is the original. This is what we would call the pre-image, if you remember back from our transformation unit, and it turns into this image. So this is the, remember, before, and this is the after. Now, in the end, they give us all the coordinates, but who really cares? What is the scale factor of the dilation? And remember, the scale factor of a dilation was really the fraction that our image got bigger, or it could have been the fraction that it got smaller. Now, you can tell in this problem that if we started big and we went smaller, then the dilation, the scale factor, is going to be something less than 1. It's going to be some fraction. If you look at our answer choices here, all of these values are less than 1. So there's none of these that we can really eliminate. You know, if one of these had said like 1.75, then I would go, yep, can't be that. I know it's getting smaller, and 1.75 is really saying it's getting bigger. So we can't get rid of any of those. So honestly, at this point, we just have to focus on one side of our pre-image and then its corresponding side in the image. So I think it would just be easiest. Let's talk about side BC up here. How long is side BC? And you might go, oh, it's 3 units long. 1, 2, 3. And I wouldn't blame you for saying 3, but notice the axis down here. It doesn't count by 1s, it counts by 2s. Ooh, so this really has a length of 6. And then its corresponding side, if BC is the middle 2 letters, then QR the middle 2 letters. Well, that's this piece. And it looks like it's got a length of 1.5. But remember, this isn't 1.5. We got to double that because our scale is by 2s. So the 6 turns into a 3. So if we had a length of 6 for BC, then what would we multiply, aka the scale factor, so that we end up at a QR of 3. So we could divide both sides by 6, and our scale factor is 3, really ugly 3, 3/6, which is 1/2, which is our 0.5. So our scale factor is nothing more than the ratio of our sides. Now, I could have done the same thing with AB and PQ, but to be honest, I can't count that on this graph. It's a diagonal piece. I'd have to use the Pythagorean theorem. So why would I use the Pythagorean theorem when I can clearly just count these 2 pieces? Or you could have went with those 2 pieces. But they're longer, so why count more when you can count less? I played smart there. All right, next up. Triangle ABC, so here's triangle ABC, is similar to triangle DEF. We already have similar triangles established. Awesome. We are also told that the area of this particular triangle ABC, the area is 56 inches squared. We're asked to figure out what is the area of the smaller triangle. Well, consider this. We know the area has to be less than 56 inches squared, right? Now, there's two different ways to treat this problem, and I'm going to show you both. One way I think is going to be a lot more intuitive than maybe the other, all right? So the first thing I'd consider is, how did we used to find areas of triangles? And once upon a time, we used to use 1/2 base times height. But we also had to discuss what was true about the base and the height of our triangle was that they had to be perpendicular to each other. And so I don't have perpendicular sides in here, but if I wanted to call the base one of these three sides, I could, for instance, call the base, what if it's the 16? Okay, so let's call the base the 16 here. Then the height would have to be perpendicular to it, and it would have to start up here at A, and we'd have to drop down and make it perpendicular. So here's the height. So notice if I know the area is 56 and I'm calling the base 16, then that means in the end I only have one variable in this area equation. I'd have 56 equals 1/2 base 16 times height. So half of 16 is 8 times h. If I divide the 8 over, I know that the height of this triangle must be 7. Okay, so where do we go from there? Well, if these triangles are similar to each other, that means all of the sides are proportional to each other. But not only that, but every length aspect of the triangles are proportional. So even though this 7 for the height isn't one of the three sides of triangle ABC, its height will be proportional to the height of the other triangle over here. And we can use that. Now, the first thing I got to establish in the other triangle is which side, the 8 or the 12.8, really corresponds to this base of 16. Well, if BC is 16, that's the last two letters, it's going to correspond to side EF, which just happens to be this piece. So, if I draw in its height, so let's call this H, I can now set up and figure out, well, what is the height of this triangle? So I know that the 16 and the 12.8, they're corresponding sides to each other. So I could set up a ratio with those. 16 over 12.8 is going to be equal to, now I can talk about the height of this triangle, 7, over the height of this triangle, which I don't know. And so now I can cross multiply this. And I get 16h equals, need a calculator. 12.8 times 7 gives me 89.6. And then divide the 16 over, and I get that the height is 5.6 exactly. So now that I know the height of this triangle is 5.6, and I've already established that the 12.8 is the base, now I can do 1/2 base times height. So let me clear some space off up here. We can now say the area 1/2 base times height. We're using the 12.8 as the base. We figured out its adjusted height is 5.6 proportionally. So now 1/2 times 12.8 times 5.6 gives us, drumroll please, exactly 35.84 inches squared. Now, at the beginning of this problem, I said there's two different ways to do this problem. This is what I would consider the more intuitive way of doing the problem, but it's also the longer way of doing the problem. So I'm going to throw at you the shorter way of doing this problem, but it's not as intuitive. And it kind of relies back on our dilation chapter. And there were some problems that we did back then that really we could apply to this same problem. Okay, so let me clear this off. We're going to start all the way over from scratch here. So we knew this area was 56 inches squared. We needed to figure out what this area was. Now, we can look at the side ratios. So we either have this 16 matches with this 12.8, or we haven't used the 10 and the 8. And I would maybe want to use the 10 and the 8 only because the 12.8 is a decimal. Let's be honest. So let's use the 10 and the 8 as a ratio. So the ratio of the sides, is it thinking? Oh, there we go. Now I get to use my pen. The ratio of the sides between these two triangles is in a 10 to 8 ratio, which if I simplify that is in a 5 to 4 ratio. So for every 4 units that I have in this triangle has 5 units instead. Okay? Now, we can't, unfortunately, use this ratio and set up an area ratio. So we're not going to be able to do this. And the reason why we can't do that is because this is a one-dimensional ratio. This is a ratio of two sides, which are one dimensions. And the 56 and the x, if I call this area x, this is a ratio of 2 dimensions, right? Because area is like base times height. We have two values that are being multiplied to get area. So I can't do this ratio, but it's really, really close to being that, all right? So if I need my dimensions to match, then I could turn this one-dimensional ratio into a two-dimensional ratio. And in order to accomplish that, I would need to square this ratio. And if I square a one-dimensional ratio, it now becomes a two-dimensional ratio. So now, I'm just going to write this over here. 5 squared, 25. 4 squared, 16. So now I'm going to ignore this. Let me just erase this part now. And slide this. No, it's all connected. Awesome. Let me just rewrite this over here. Now, I can cross multiply this. And I can have 25x equals, I don't know what 56 times 16 is, something big, 896. And then if I divide both sides by 25, then I get, oh my gosh, 35.84, which was the answer that I got previously. This was a lot shorter, but it's not as intuitive. So whichever way makes the most sense to you, go for that route, we'll say. All right, the next problem. Calculate the, oh my gosh, is that trig? Are we talking trig here? The sine of c? Oh boy, oh boy. I didn't think we were doing trig this unit. Don't fret, we're not going to get into the big trig. What you do need to remember, though, is what the definition of sine was. And sine was the opposite over the hypotenuse. Okay, so let's go look at the opposite and hypotenuse of angle C down here. So here's angle C. The opposite side would be here, which is side AB, and the hypotenuse is AC, which, shoot, we don't know either one of those numbers. Awesome. I guess the problem's broken. We can't do it. Wrong. What we're going to do instead is discuss first what's so special about these two triangles. Notice both triangles are similar by angle-angle similarity, which means if they are similar, so triangle ABC is similar to triangle DEF by a very hopefully obvious angle-angle similarity, that means that the sides are proportional. And you might ask, well, why are we dealing with sine, cosine, tangent? Well, sine, cosine, tangent are ratios of sides, which is all we've been dealing with in this chapter with proportional sides between two similar triangles. So the sine of angle C should also be the same as the sine of its equivalent angle. What else is angle C equal to? Angle C is equivalent to angle F. So if we want to figure out what the sine of angle C is, we just need to figure out what the sine of angle F is. So now let's look at the smaller triangle. So we need to know what is the opposite side and what is the hypotenuse in the smaller triangle. So the opposite side, sweet, that's 20. The hypotenuse is not known, but we know two sides of this triangle. So how could we get the third side of a right triangle if we know two sides? Did you say Pythagorean theorem? Because I think I heard you say Pythagorean theorem. So we could set up the Pythagorean theorem so that we can get the hypotenuse to set down here and then simplify this ratio, and then we'll finally be done. So if we had 10 squared plus 20 squared, that's supposed to be a squared, I promise. There we go. Equals, we'll just say hypotenuse squared, c squared. So 100 plus 400 makes 500, which is the hypotenuse squared, square root the 500. The ideal breakdown scenario would be 100 times 5 to get us 10 root 5 is the hypotenuse. So if I put 10 root 5 down here, then we're going to have to simplify. We may simplify the 20 and the 10. 20 divided by 10 is going to give me 2, but that 2 is going to be up in the numerator, not down in the denominator. And then we got 2 divided by root 5. But it doesn't end there. Because remember, once upon a time, we can't have square roots in the denominator. So we rationalize the denominator by multiplying the top and the bottom by that square root in the denominator. And then we just multiply our fractions straight across. So 2 times root 5 is 2 root 5. Root 5 times root 5 in the denominator just gives us 5. And now we have a fully simplified fractional square root answer of 2 root 5 over 5. Wasn't that a fun problem? You got to use trig. You got to use Pythagorean theorem. We got to use, just all sorts of stuff. I mean, fun times, right, guys? Fun times. Oh, hey, look, another one. Awesome. And there's no picture. Sweet. So we get to draw a picture. So we are told right triangle, WXY. So let's draw a right triangle. Right angle. And I don't really know how I should label WXY because I don't know which one's the 90 yet. But it says it's similar to triangle DEF. So let's draw another triangle, another right triangle. And then they give us some information here. Angle F is the 90-degree angle. So let's say angle F's the 90. But that now also means if F is the 90, then Y must be the 90 in the other triangle. Perfect. All right, what else do we know? DE is root 113. Well, where does D and where does E go here? And to be honest with you, it doesn't matter. We'll just pretend that this thing's not drawn to scale, so who cares? There's 113, square root of 113. DF is 7, and EF is 8. Now, you might go, but it looks like the 7's longer than the 8. True, but who cares? Not drawn to scale. Okay, you can make a little note off to the side. Not drawn to scale. And then, there we go, little emoji. All right, so now, which expression represents the cosine of W? Well, we still got to figure out which one was W and which one was X over here. But if I put D up here, D matches with W. So W is going to go up here, which means Z has to go down here. So the cosine of W, well, now we got to remember, what was the definition of cosine? Cosine is the adjacent over the hypotenuse. But we don't know any sides in this triangle. Not a problem. Not a problem, because we're told these triangles are similar to each other, which means we can swap out the W for its equivalent angle, which is D. So the cosine of W is going to be the same ratio as the cosine of D. So now we just got to focus on what is the adjacent and the hypotenuse of angle D. So what is the adjacent side of angle D? Well, the adjacent side's either the 7 or the root 113, but the root 113 is the hypotenuse. So that means the adjacent is the 7, and over the hypotenuse, root 113. Now, typically, I would say for this, we're going to need to rationalize it, but notice in this particular problem, they did not rationalize. So the correct answer would just be A in that case. So there are two examples, this one and the last one, in which we use trig to talk about ratios of sides in two triangles that really are going to match up to each other. But instead of knowing any of the sides in one, we can go over and represent our ratio in the other triangle.